Good morning to all of you. First of all, I want to introduce myself. Myself Ankit Acharya, working as an assistant professor in Hasmukh Goswami College of Engineering. And today my content is GTU question paper solution of the subject of vector calculus and linear algebra of June 2009. So up to question number 3D we already see. So let's start with question number 3E. Find the rank and nullity of the matrix A, that is equal to 2 0 minus 1 4 0 minus 2 0 0 0. So first row is 2 0 minus 1, second row is 4 0 minus 2, and the third row is 0 0 0. And this question asking 2 marks. So what first of all we have to do, we have to convert this matrix into a row echelon form. So here is the matrix A is equal to 2 0 minus 1 4 0 minus 2 0 0 0. So what is our the first process? So this is our leading entry, 2 is our leading entry of the first row. So we have to multiply first row with minus 2 and add into the second row. So that's why this element, this 4 become 0 now. So here is the process, we can write in this manner r12 minus 2, that means we multiply first row with minus 2 and add into the second row. So the first row is as it is 2 0 minus 1. The second row become, when we multiply first row with minus 2 and add into the second row become 0 0 0, and the third row is as it is 0 0 0. So now you can say that this matrix is in row echelon form, right? In this row echelon form matrix, how many non-zero rows? We have only one non-zero rows. Okay, so that's why the rank of A, that is equal to number of non-zero row, that is equal to 1. Okay, because the definition of rank, that is exactly the number of non-zero row in the row echelon form matrix of the given matrix. So here is the rank of A is equal to number of non-zero row, that is equal to 1. Now by rank nullity theorem also we have to find nullity of the given matrix, and to find nullity, now we already know the rank of the matrix, and to find nullity we use rank nullity theorem. Now what it says, rank nullity theorem? Rank nullity theorem says that rank of any matrix plus nullity of any matrix, that is equal to the number of columns of the given matrix A. So we already know that the rank of the matrix, that is 1, plus nullity, that is equal to number of columns of A, that is equal to 3. So nullity of A is equal to 2. Okay, so the nullity of A is equal to 2, correct? So here is a complete the question solution of this question asking 2 marks in that GTU question paper. Next is question 3 or. So this is question 3, first question 3 complete. Next is question 3 or. Let V is equal to xy in bracket xy, where xy belongs to R, where y greater than 0. So definitely this is a subset of R2 because it has two coordinates x and y, both are real numbers where the second coordinate is greater than 0. Let AB and CD belongs to V and alpha belongs to R. Define AB plus CD, that is equal to A plus C, comma B into D, and alpha into AB, that is equal to alpha into A, comma B raised to alpha. So using this addition and scalar multiplication, we have to prove that the given set is a vector space. What is our addition? Just I again repeat, AB plus CD, that is equal to A plus C, and B into D, and alpha, where alpha is any scalar, alpha into AB, that means scalar multiplication is defined in this manner, alpha into AB, that is equal to alpha into A and B raised to alpha. So this question asking 5 marks, and we have to prove all the 10 conditions, right, for the vector space. So the first 5 conditions are for addition, and the next 5 condition are for scalar multiplication. So first condition is closedness. I want to explain what is the definition of vector space. First of all, the first 5 conditions are for addition and the next 5 conditions are for scalar multiplication. The first one is closedness, that means if u v belongs to set V, capital V, then we have to prove that u plus v, that is also belongs to V. Then associativity, u plus v in bracket plus w, that is equal to u plus in bracket v plus w. Then commutativity, u plus v is equal to v plus u, that is true for all u v w, right? All u v belongs to the capital V, where v is a set. Fourth condition is identity, that means there exists some identity which is also in the set, such that u plus that identity theta, sometime we call theta or sometime we call 0, u plus 0, that is equal to u, and similarly 0 plus u, that is also u. 0 is a additive identity, right, of the given set. Next one is inverse, addition inverse of addition, that is u plus minus u. We can find such minus u belongs to V, where V is a set, such that u plus minus u, that is equal to 0, where 0 is the identity element. So if these 5 conditions are satisfied, then we can say that the given set is a satisfied all the first 5 conditions for addition. Next 5 conditions are for scalar multiplication, in which the first one is that means the sixth one is alpha into, if alpha is any scalar, then alpha into u, where u is any vector of set V, then alpha into u belongs to also V, right? Then u plus then alpha in bracket alpha beta into u, that is equal to alpha in bracket beta into u, that is equal to beta in bracket alpha into u. Then distributive law, that is alpha into u plus v, that is equal to alpha into u plus alpha into v. Then alpha plus beta into u, that is equal to alpha into u plus beta into u. And the last condition is 1 into u, that is equal to 1 u, right? So if this all the 10 conditions are satisfied, then we can say that the given set is a vector space under the addition and scalar multiplication defined in the set, right, defined on the set. So exactly we have to prove here all the 10 conditions one by one. We have to check all the 10 conditions one by one, and if all the 10 conditions are satisfied, then we can say that the given set is a vector space under the addition and scalar multiplication, which is defined in the statement. So let's see, we check one by one all the 10 conditions. Here is the first condition, u is equal to ab, v is equal to cd, and w is equal to ef belongs to v, right? So first of all, we take 3 vectors, randomly 3 vectors which all are belongs to v. So u plus v. Now just again try to understand the first of all set. What type of set we have? We have this type of set xy, where xy is real number, but the second coordinate must be greater than 0, right? So in this u v w all are belongs to v, so you can understand that b greater than 0, d greater than 0, and f greater than 0. Okay, now u plus v, that is equal to ab plus cd. Now we define in this manner, right, addition in this manner, a plus c, b into d. So that is equal to, can be written as a plus c, b into d. Okay, now b and d both are greater than 0, so you can understand that b into d, that is also greater than 0, and this is any real number a plus c. So definitely it satisfied the condition of the set, so that's why u plus v belongs to v. Okay, next is u plus v, that is equal to ab plus cd, that is that can be expressed as a plus c, b into d, using this definition, that is equal to a plus c. Now a plus c can be written as c plus a, because in real numbers we already have commutative property, right? And b into d, that is can be written as d into b. So this is equal to v plus u. When we distribute them, that we can write c plus cd plus ab, so that is v plus u. So u plus v, that is equal to v plus u. Now next one, in bracket u plus v plus w, that is equal to ab plus cd plus ef. Just see this 4 steps, right? You can easily understand. A plus c, a plus ab plus cd plus ef, in bracket ab plus cd. Now using this our definition, using on this bracket first of all, so we can write a plus c bd plus ef. Now again use the definition of addition, a plus c plus e bdf. Now a plus c plus e, that can be written as a plus in bracket c plus e b in bracket df. Okay, that can be written as ab plus in bracket c plus e df, and that can be written as ab plus in bracket cd plus ef. So easily we can prove that associative property is satisfied for this set V. Okay, now what is our identity? Here we define identity or denote we identity element in this manner 1. Okay, we denote our identity element in this manner 1. Now 1 is equal to 0 1. Why we take this 0 1? Just try to understand. Definitely 0 1 belongs to V, because the first coordinate is real number and the second coordinate is greater than 0, right? So 0 1 belongs to V. For every u is equal to ab belongs to V, u plus 1. What is our u plus 1? That is equal to ab plus 0 1, that is equal to a plus 0. Using the definition of addition, a plus 0 b into 1. So that is equal to ab, that is equal to u. So u plus 1, that is equal to u. Similarly we can define or we can prove it that 1 plus u, that is also u. Okay, so thus u plus 1, that is equal to 1 plus u, that is equal to u. So this 1, what is our 1? 0 1 is our additive identity. Okay, that is our additive identity. Next condition, for each u is equal to ab, there exists minus u equal to minus a 1 upon b belongs to v, such that u plus minus u, that is equal to ab plus minus a 1 upon b, right? Now how we define addition? Just again I repeat how we define addition. A plus ab plus cd, that is equal to a plus c bd. So when we add this two vector ab plus minus a 1 upon b, that is equal to a minus a b into 1 upon b. Okay, that is equal to 0 1, that is exactly our identity element 1. Okay, similarly we can prove minus u plus u, that is equal to 1. Okay, similarly we can prove minus u plus u is equal to 1. Now so the first 5 conditions for addition are easily satisfied. Next condition, for any alpha belongs to R and ab belongs to V, alpha into ab, that is equal to alpha into a b raised to alpha belongs to V. Okay, so let alpha belongs to R, then alpha into u plus V, that is equal to alpha into ab plus cd, that is equal to alpha a plus c b into d. Just you can easily understand what it says, right? Alpha into a plus c. Now here we use scalar multiplication, that is alpha into a. Okay, first of all try to understand this property, where for any scalar alpha belongs to R and ab belongs to V, alpha into ab, that is equal to alpha into a, right? Now that is definitely real number, but the second coordinate must be a positive real number, right? And it also positive real numbers because of b is greater than 0. So b is positive, alpha is any real number, so definitely b raised to alpha is always positive because of b is positive, right? B is positive number and alpha is any number, either it's positive or negative, or either it's 0. right? In 0, that is also b raised to 0, that is 1 for b greater than 0, correct? So for any scalar alpha, b raised to alpha must be a positive number, so that's why this belongs to b. It satisfied the condition that the first coordinate is real number and the second coordinate is greater than 0. Okay, now let alpha belongs to R, then alpha into u plus v, that is equal to alpha into ab plus cd. Alpha into, just we use the property of we use the definition of addition for two vectors a plus c, b into d. Now we use scalar multiplication, that is alpha into a plus c, and here bd raised to alpha. Now alpha into a plus c can be written as alpha into a plus alpha into c, and bd raised to alpha, that can be written as b raised to alpha d raised to alpha. So that can be expanded, that alpha into ab, because of alpha a b raised to alpha, that is alpha into ab, and alpha c d raised to alpha, that is can be written as alpha into cd, right? So alpha into u plus alpha into v. So we can easily prove that alpha into u plus v, that is equal to alpha into u plus alpha into v. Okay, so the seventh condition for the vector space is also satisfied. Here is the next condition, 8. Let alpha beta belongs to R, then alpha plus beta into u, that is equal to alpha plus beta into ab, that is equal to alpha plus beta into a into b raised to alpha plus beta. Okay, alpha beta are scalar, so alpha plus beta is also scalar. So alpha plus beta into ab, that can be written as, we use the definition of the scalar multiplication. So alpha plus beta into a into comma b raised to alpha plus beta. Now alpha plus beta into a can be written as alpha into a plus beta into a, and b raised to alpha plus beta, that can be expressed as b raised to alpha into b raised to beta. So when we expanded that terms, we get alpha into a b raised to alpha plus beta into a b raised to alpha, okay, b raised to beta. So that is equal to alpha into ab plus beta into ab, that is equal to alpha into u plus beta into u. Okay, so we can also prove that alpha plus beta into u, that is equal to alpha into u plus beta into u. So the distribution